Okay, thank you for the introduction, and I will present you our work on spoken term detection. It is pretty related to the work which Bolaj presented before, but I will show you some differences here. So this is the motivation slide. I don't know if it works. So if we have some huge audio collection and some search term, we can say that we would like to search the search term in the audio collection, and we can have just the audios, we can have the recognized one-best hypothesis of the audio collection, or the phoneme lattices, word lattices. And the same for the search term, we can have the audio, or the in vocabulary word, or the graphemic sequence or phonemic sequence of the search term. The graphemic sequence of the search term is more suitable for the users of the system, because the users are not used to the phoneme representations and the phonemic rules and so on. So here we have two extreme tasks. The first one is the query by example, and the much easier task is the search in the inverted word index, where we just use the word lattices from LVCSR and we perform the in vocabulary search of the search term. And we are focusing on the task where we have the graphemic query, and we would like to search the term in the set of phoneme lattices. And another motivation for us is our target task. We are working on oral history archives, and mainly on the USC Shoah Foundation Visual History Archive, which is the archive of Holocaust testimonies. And the archive contains a huge number of testimonies from people who survived the Holocaust machinery and so on. And the collection of such archive was initiated by Steven Spielberg. So here I have a small motivation video.
Making Schindler's List was an experience that truly changed my life. Filming just outside the gates of Auschwitz-Birkenau, I realized that had I been standing on that exact spot at a different point in time, I more than likely would have been killed too. I remember talking to a lot of survivors during the production. How did you survive?
By miracle.
It was one of the first moments that made me realize that there were many, many stories that needed to be told. That's how the Shoah Foundation began. It began because my wanting to continue Schindler's List.
So we are working with the data of from such a huge collection. The collection has about 55,000 testimonies in 43 languages. And we work mainly on English, Czech, and Slovak parts, which we have indexed, and we deployed the search engine, which is publicly accessible at the Charles University in Prague, where they have the access center to the visual history archive. And here is some brief overview of the timeline, how we started to search for OOE words in such a huge archive. In 2010, we implemented the simple in vocabulary word search, and also the heuristic method for searching of vocabulary words. It was based on pre-indexed triplets of phonemes, and we used the heuristic scoring of putative hits. Then in 2016, we implemented the neural network-based method. It uses the Siamese networks and the contrastive loss function to train the network, but the network was used just for scoring of the putative hits, and we still used the heuristical search method for determining the putative hits. And now we present the fully neural network-based method for spoken term detection, and it allows to jointly detect the putative hits and assign the posterior probabilities of such hits. And this is the baseline architecture, the Siamese neural network architecture. And the architecture has two subnetworks. The first one processes the graphemic sequence of the query, and the second one the output of the speech recognizer in the form of a phoneme confusion network. And both sides are mapped to the embeddings, and the corresponding score is computed as a distance of such embeddings. And one of the drawbacks of such method was that the putative hits were determined completely heuristically. So we proposed some modifications and we implemented them. The first thing which we kept is the implicit G2P modeling, because the network which maps from the graphemic representation of the search terms to the phonemic embeddings allows us to model the grapheme to phoneme mapping or grapheme to embedding mapping. And it is very important, especially for the out-of-vocabulary words, because for the MALACH archive, we have a very complicated situation because the people are elder, they are talking about some in some hard emotional state, and also they are talking, for example, in English, but their native speech is Czech, and they are talking about cities in Poland. So this is a rather complicated task. And next, we kept the dual structure of the recurrent neural network, and we replaced the contrastive loss function with a simple binary cross entropy, and it determined the spoken term detection process, because we just simply run the recurrent neural network, we produce the embeddings, and then we compute the posterior probabilities. And what we used is the unsupervised network training, where we use the fact that we have a large collection of audio data. So we blindly recognize the audio data with LVCSR on the word level, and at the same time with the phoneme recognizer, and we obtained the aligned word hypotheses and the corresponding segments of the phoneme confusion network. So we were able to automatically generate the training data. And the proposed architecture has the same dual structure. Here we produce the phoneme embeddings from the phoneme confusion network, and also the query embeddings from the graphemic representation of the query. What is important is that we produce the phoneme embedding for each segment of the phoneme confusion network, and then we simply generate the per segment probabilities by simply computing the dot product of the phoneme embedding and the query embedding, and applying some sigmoid calibration. What we used additionally is the feature of multiple query embeddings. This feature allows us to provide more expressive power to the model without increasing the computational complexity. It has the same number of parameters, and we use first embedding for the first half of the query, second embedding for the middle part of the query, and last embedding for the last part of the query. And then we obtain 3 unnormalized scores, and we take just the maximum of such scalar values. We also use the skip connections, and we also use some output smoothing with a simple mean filter. And here is a sample output of the system. If we have the real pronunciation, my name, real utterance, my name is Rosie Greenfeld and something. And we would like to search the word Greenfeld, the green one. Here we have the peak in the posterior probabilities. And the different shades of the green color are corresponding to the first, middle, and last part of the query embedding. And the same for the word Rosie. And also I have to note that the system is able to catch some contextual information from the data, because we use 2 very similar words, the name and named. And based on the context, the posterior probability of the word name is much higher than the black one for the word named. And the training of the system is very simple, because we, from such real utterance, we randomly sample the word Greenfeld, and we use the target, which forces the network to output 1 on in the time span when the word is present, otherwise 0. And we provide no assignment of the first, second, and third query embedding. We just take the maximum value. And we have some details about the training because the query is fed from both sides. We use some data augmentation, and also we train from just words which are recognized with high confidence. And really important detail is the estimation of minimum putative hit length in the number of phoneme confusion network segments, because therefore we are able to ignore peaks that are shorter than the minimum length. We use a multitask training here, and we are able to avoid the highly probable partial matches of subwords of the search term. And here we have some dataset statistics. We experimented with English and Czech data. We have in vocabulary terms and out of vocabulary terms. And if we look at the results, we can see that the baseline methods, the heuristical empirical method and the Siamese neural network were outperformed on English and Czech by a large margin. And you can see that the splitting of the search query into the first, middle, and last part provides a big improvement in the NTWVV method metric from 63 to 67% on English. And also we experimented with the output filtering window length. Longer and shorter windows does not provide any improvement. And also the LSTM skip connections add some improvement, and they mainly stabilize the training process and provide better convergence of the system. Here we show the numbers for in vocabulary terms and out of vocabulary terms, and the same is for the test data. And we also show the results where we combine the out of vocabulary search based on LSTM networks with the LVCSR system, where the in vocabulary words are searched in the inverted index and the out of vocabulary terms are searched in the phoneme confusion network. So here the combination provides the best results. And just a few words about our future work. And it's related to the speed of the search and the complexity of the search. And for us, it's very important to search really fast through large archives. And we can say that the phoneme embeddings could be pre-computed for the whole archive. And we are trying to quantize such embeddings and provide some quantization codebook of the embeddings. At the query time, we can just determine the quantization codes which we want to search and the minimum length, and then we would be able to reduce the task to simple regular expression search in the database. We can pre-index the database using some prefix index or something like that. And we also want to generalize the method to query by example and hybrid search, exactly like Bola had said. So this is our future work. So thank you for your attention. And if you want some more details, some math equations and so on, it is provided in the paper.
Thank you for this presentation. Do we have any questions in the room? No, there's no question. Well, I can ask some. Yeah. So how did you choose the keyword on this database?
Yeah, the keywords were automatically generated from the reference transcriptions, and they were chosen based on the LVCSR vocabulary. So they are not in the ASR vocabulary, and they are also not the subword or near match of the words in the ASR vocabulary. And also there is a criterion that the word is not on the word boundary of two words. The term.
But is it based on frequency? How did you choose them?
Yeah, the out of vocabulary terms are the words which occur just once or twice in the data, and in vocabulary words they occur more frequently because, for example, for English you have several words repeating, but we also had the limit on the word length. So
they can be proper name or common name. They can
yeah, exactly. So it's completely unsupervised.
Okay. I have another question about, do you think this technique can be used for with a multilingual data set?
Yeah, I think so. We would like to try it, to train multiple languages, because I don't see any problem with the multiple. Yeah, we have the models for which uses separated data, but there is no problem with trading in the multitask manner and multilingual manner. And there is a question if we could give the system the source language or not, and the same for the query, because some words have the same graphemic representation in multiple languages and so on. But it's just the design query, a design question.
Okay. So still no more question, no question in the room? Ah, yes.
Hi, thank you for the presentation. I was wondering, do you have an idea how sensitive is your system to the performance of the large vocabulary speech recognition? And can you quantify what is the performance of the system that you're using?
Yeah, it was in the table, but we have roughly 20% word error rate for both languages. And it's not so sensitive because we use the filtering of the recognized words based on the confidence. And also the data augmentation, where we merge subsequent words which have large confidence. So if you have a really bad ASR system, you just need more data to obtain sufficient examples for training such system. Yeah, sure.
Do you want to use the microphone? Yeah, we have time.
So you use confusion network, okay,
yeah,
as input.
Mm-hmm.
So the performance depends on the length of the bean in the confusion network. Did you do some experiments?
Exactly, but yeah, we were used to use the phoneme lattices, but it's a really hard task how to parameterize the lattices into the neural network. So we used the confusion networks, which are simple list of lists, and we also take just the first 3 hypotheses from the confusion network. It simplifies the representation of the confusion network segment, and we don't take not only the phoneme on the edge, but also the posterior probability of the phoneme and also the duration information. So this composes into the feature vector.
Okay, there's no more question. We can thank the speaker again.
Thank you.